In this section, we're going to cover discontinuous forcing functions. Essentially, if you think about what we've been covering up until this point, 6.1 and 6.2 is how do we take a Laplace and inverse Laplace and apply that to a differential equation. And then 6.3 was, okay, what's the step function and how do we deal with more advanced Laplace transformations? And then now 6.4 is like, let's just combine that all into one section and make that into a problem, which is like solving an IVP, but now it can be equal to a step function or a piecewise function. So that's really the big difference. And what I would recommend that you really focus on first in diving into this section is like setting up the Laplace transformations. And what I mean by that is we kind of have two goals, right? We want to find y of s, the Laplace equation, and then y of t through the inverse. Getting to y of s is half the battle. And sometimes that's the question that they want, right? What is y of s? And then other times they may ask you to go further and apply the inverse Laplace transformation. So do recognize that there's two aspects to this problem. Taking the Laplace transformation and algebraic manipulations, and then undoing them, getting back into the differential equation realm, right? So just an important Laplace to remember, because we're going to use this a few times in this section. The Laplace transformation of f of t minus a times u of t minus a will be equal to e to the negative a times s, f of s, right? Where f of s is equal to the Laplace transformation of f of t. This isn't to say that this is the only one that you need to remember, but I'm telling you right now, because we're dealing with step functions and all of these problems, you're going to use that one pretty much in every single one of them because of the fact that there's a step function to be dealt with, right? So that's a big one that you're going to want to remember. And then some other things that we want to remember, right? Just important formula. And that is how do we convert something into a step function, right? So if f of t is equal to g of t and h of t for some value of a, or 0 to a, and then greater than a, then as a step function, this is going to be equal to g of t minus g of t times the step function at a plus h of t, and that's going to be times u of t minus a, right? You're mostly going to convert step functions, piecewise functions into step functions. And that's what makes these a little bit more challenging is not even the differential equation solving, it's just converting a step function correctly. Sometimes they do just give it to you directly as a step function, and sometimes that could be a little bit more confusing because if you're so used to doing it one way, you got to remember, oh yeah, this really just means piecewise function, right? So just keep those things in mind as we're doing these problems. But of course, you always want to remember that the Laplace transformation table is still in play. We can use that at any point during this because we're not restricted to basically certain amount of functions. And partial fraction decomposition is also allowed at any point depending on the problem. So we'll just copy that and put it over here just in case I have to reference it later. Okay, so the first few examples, we're not going to solve an IVP because, again, solving the IVP is just doing what we've been doing for a while now, which is taking inverse Laplace transformations. Let's set them up because setting up is half the battle. The other half is partial fraction decomposition and manipulations. So let's start off with a small example. Find y of s. So that's just telling you take the Laplace and isolate y of s. So we don't have to go all the way to the y of t. And so our differential equation would look something like this. And let's do 9 and 0. And then our boundaries will be from 0 to 8, and then anything bigger than 8. Given y of 0 equals 0. Sorry, incorrect. That was the wrong one. 7. And then y prime of 0 is equal to 0. That's the one equal to 0. So step number 1 is formula. So because you're taking the Laplace transformation of derivatives, right, you should still remember those ones because you're going to have to do that for almost every single problem, if not every single problem, really. So if there's any Laplace transformations you should write down, is this one. So s squared y of s minus s y of 0 minus y prime of 0. And then we don't need y prime, we just need y, which we know is just y of s. Capital Y of s. Like that. And that's all we need for now. I mean, I could write down the formula for step functions, but that's not something we really need to write down if we're not just solely focusing on step functions. So then step 2 is going to be Laplace both sides. So Laplace both sides. So the Laplace transformation of y double prime plus 49y is equal to, so when you have a function like this, a lot of the times they might just call it like f of t. So in the directions, they might say f of t, and then they off to the side define what f of t is. So I'm just going to define it as f of t, just for the sake of, simplicity. I don't have to write down that whole piecewise function. And so we Laplace both sides. Again, however much work you want to show here, I mean, you could really just combine a lot of these steps into one step. When you start combining steps and, cutting things out, that's just the human desire to optimize, and that's a good thing here. So, whatever you want to do. And then step 3 is we're going to evaluate and sub in. Well, actually, before we do that, this actually could have been step 2, but let's call it step 3. Convert f of t into a step function, right? In reality, this should have probably been step 2, but it's fine. So we want to convert this into a step function. And so the easiest way of doing that is to kind of follow our formula, g of t, h of t. And so we write down the first function, 9 minus, right? So we subtract by the same function, 9 u of t minus 8, and then plus 0, and then it doesn't matter. 0 times anything is 0. So that's our step function. So f of t is equal to 9 minus 9u of t minus 8, right? Yeah, that's good to go. And so then step 4 is now we are going to evaluate the Laplace transformation. So evaluate the Laplace transformation and plug in initial conditions. So the Laplace transformation of y double prime plus 49 Laplace transformation of y is equal to the Laplace transformation of 9. And then we have minus 9 Laplace transformation of the step function at 8. And so according to our formula, this will be that. So we have the second derivative, and then we have sy, that's not correct, y of s minus y of 0 equal to the Laplace transformation of 9, or any constant, is that constant over s, so 9 over s, not to be confused with an a. And then the Laplace transformation of a step function is going to be e to the negative a, so remember that this is a right here, so 8s all over s, like that. So that is the Laplace transformation of our step function. So that's really the big change from 6.3, is the right side is a little bit more annoying to deal with, but other than that, it's the same process. So then we plug in our initial conditions. I believe that was 7 or 3. No, it was 7. And that was 0. And then we get 49 times s, y of s, minus 7, and 9 over s, minus 9e to the negative 8s over s. Can you combine those together into one thing? You can. I'm just waiting. I could do it now or I could do it later. It's just kind of like just wait and see. Maybe I don't have to. And so then we get s squared y of s minus 7s plus 49s y of s uh, minus, and then 49 times 7 is something. Except I made a mistake, right? This is the Laplace transformation of y, not y prime. That's just my brain instinctually thinking, when you do a lot of like second order with all three terms, your brain will automatically just go into this autopilot mode where it does the minus y of 0 because it expects it to be there. But the reality is that was incorrect. So it's a common mistake. It's got to avoid it, honestly. So thankfully, we don't have to deal with that. That'd have been a nasty number. Constants are your biggest enemies in mathematics. They are what cause problems to be, much more difficult just because they're kind of hard to deal with. So we have y of s, right? So step 5 now is to isolate y of s. This is the actual, final step that we want. So s squared y of s plus 49s y of s. And then I'm going to add that 7s to the right side, right? So and then plus 7s. We moved it over. And all I have to do now is factor out a y of s. And we get s squared plus 49s is equal to, except there is no s because it was not the first derivative, so don't need to carry that around. There we go. A lot of mistakes on the first example, but that's okay. At least we caught them. And then divide over. Now let's go to the next slide since I have to say anything anyways. So y of s is equal to 9 over s minus 9e to the negative 8s over s plus 7s. Want to make sure that's correct. Yep. And then all divided by s squared plus 49. Now, this answer, 100% correct. There's nothing wrong with that answer. It's just not simplified. So if anyone was looking at this, they'd just be like, okay, what's going on here? So a couple of things you can do to simplify. When you divide a fraction, like let's use capital letters here, A over B divided by C, you can remember that fractions, if you're dividing, you can flip them and multiply. So this would really just be AC over B. And if you're wondering why, well, I mean, technically anything can be divided by 1. And so what you end up getting is A over 1 times C over B, which is then AC over B, right? Like that's the justification for it. But I'm just kind of remind you that of the fractional properties. And then we can combine fractions if we want. But, let's just do this. 9 over s times s squared plus 49 minus 9e to the negative 8s over s times s squared plus 49 plus 7s over s squared plus 49. And then if you want to combine fractions together, you can, as long as they have the same denominator, which, the first two do, except that's a minus sign, not a subtraction. And if you're wondering, like, well, how far do I have to go? It depends. Most homework systems, at least calculus or differential equations, they're not too picky about simplification, so they probably would accept it the very first thing. But if your homework or exam says simplified to like the lowest term, then this is probably more in line with what they want. Yes, could I combine these into a single fraction? You can, but this is one of those cases where doing that actually makes the problem worse. So in differential equations, there is a bad thing where you oversimplify because then you get into a case where you really can't do anything with it. Another example that's very common with this is that sometimes when your denominator is like, say, x plus 3 to the second power, that is the perfect form. Don't ever foil that because 9 times out of 10, you want it in that form. If you were to foil it, you would probably run into the scenario like, oh, I shouldn't have done that. I got to undo it, right? So, like, it's kind of one of those things. So, factored form, the product of terms like that, much better. So, don't foil. Always be kind of like, let me see what happens before I start simplifying. So, that's kind of the basic principle. So that's how you find Y of S. And we're just going to practice different styles and like different things that you could run into with this before we solve an IVP because solving one of these IVPs does take time. And like I said, the bigger thing that you should focus on in this section really is just getting to Y of S because that part is often more important. So let's do another example, but just kind of making it a different function. So find Y of S equal to, no, not sorry, given y double prime plus 9y equal to sine of pi times t, 0, and then you're told that t is between 1 and 0 for sine, and then it's greater than, sorry, 0 for greater than 1, given y of 0 equals 0, and y prime of 0 equals 0 as well. I do want to note that they can say this in a different way. It looks like in this class in particular, they prefer to do piecewise functions. Um, but they could also give it to you as y double prime plus 9y equal to sine of pi t u of t minus 1. So if they give it to you in step function form, in a way, they're doing part of the work for you. The problem that I notice students have with that, though, is that they're often more comfortable with the piecewise form because they usually see that more often. And then so when it's given in step function form, then people forget. Like they kind of it just so the switch up kind of makes them, blank for a moment. But remember, those are the same thing, right? These are like the same. So just giving that as a word of caution in case, you're reading it somewhere else or someone or the homework problem just asks it differently. So step number 1 is formula. So what formula do we write down? Let's just write down the Laplace transformation of y double prime. That one's really important here. Hopefully this time I do not mess up the fact that there is no y prime. And we have written down our formulas. Step 2. So this time I'm going to actually do find the step function. So find u of t minus a for f of t. They may not label it f of t, but I will just for the sake of it. So let's find the step function version of it. So y, I don't need y prime here. So our equation is the first function, so sine of pi t minus the first function times the point at which it's jumping, essentially, and then plus 0, right? I'll tell you right now, if you're wondering, like, is it always going to be 0, like, for one of them? In practice, maybe. Like, right, you turn something on and then it turns off and then it's just turned off forever, right? In the context of, like, this class, kind of, because if we, do more than, like, one or two, do more than two, it's just the problem becomes exponentially more algebraically intensive. Like it's not that it's more challenging conceptually, it's just the algebra starts to get really bad when you make these too big. So it's one of those things where in practice it'll probably be something a little more interesting, sine and then something like cosine or something. But in the context of doing a homework problem, it's like just one is already enough work. So there's our step function. Some people might write it this way, where they like maybe factor out a term and then do like 1 minus u of t minus 1. That's a possibility. Again, it's personal preference. I personally would just leave it alone. So like I personally would like not do this because I'm gonna have to Laplace it anyway. So the Laplace of that just seems like more work. Okay, so we found our step function. So then step three is Laplace both sides. Laplace of y double prime. So I'll distribute and do all of that stuff now. Plus 9 Laplace of y equal to the Laplace transformation of sine pi t minus the Laplace transformation of sine of pi t minus, not minus, sorry, times u of t minus, well, it would be a if there were no number, but it's 1, like that. So now we're going to evaluate and sub in initial condition. So it's going to be our s squared y of s minus s y of 0 minus y prime of 0 plus 9. And then this is y of s this time. We'll not make that mistake. And then the Laplace transformation of sine of pi t. So even, doing this all the time, I still don't memorize most of these formulas. So sine of pi t is a over sine or s squared plus a squared. So, and even as I said that, I already forgot what it is, but that's okay. I'm gonna guess and guess that it's that, which it is, I think. Yep. And then minus, so this one's a little trickier because this is more of a one that we just learned, right? Like I said earlier, that's going to be one of the ones that you're going to run into. It's the f of t minus a, u of t minus a. So we kind of have to do some manipulation to work with it. And there's so many ways that you can do this. One of them actually is, so this is actually not a bad option to do that alternative form if you prefer to do it that way. Or you can kind of just do a manipulation if you feel comfortable doing that. But if you forgot what the alternative form was, essentially we can do it as f of t times u of t minus a if we basically add the a term into the function when we take the Laplace transformation. And that just might make it easier for us. So again, it's an option. So which is probably what I'm going to do here. So in fact, let's see, I think we might just do this as a side example because I don't think it'll fit all very nicely in there. So the Laplace transformation of sine of pi t, set function u of t minus 1. So we're going to do our formula for this. Laplace transformation. So I'm going to do f of t, and it was u of t minus a is equal to e to the negative a times s, f of s plus a. Okay, or I mean, the way that we wrote it over there was the Laplace transformation of s plus a, but that works too. Actually, now let's just be consistent. It's the same thing, but uh, like that. So then step 2 is to identify f of t and a. So f of t is equal to sine of pi t, and then a is equal to 1. Step 3 is to find the Laplace transformation of f of t plus a. So that means find the Laplace transformation of sine of pi times t plus 1, like that. So with this one, we are going to now manipulate it using an identity, which is the following. So we're going to say, I'll write it down here. The truth is, I realize that this is probably the worst way of doing it, not because algebraic is more difficult. It's just you got to know one trig identity to do this. And when you know the trig identity, it actually becomes very straightforward, but it would also be a trig identity that most people probably just don't know off the top of their head. And it's the sum difference rule of sine. So if you were to use the sum difference rule of sine, it would be, sine of x plus y would be the sine of the first term, pi t, times the cosine of the second term, which would be cosine of pi, plus the cosine of the first term, pi t. So I'll go back and do it the other way just so that we have the one that's actually probably a little bit better. And then sine, I believe, yep, of pi. And like I told you in this class, you should know cosine of 0 and sine of 0. You should technically also know cosine of pi and sine of pi because it's the same thing, just the other way around. So from there, we get cosine of pi is -1. And then the sine of pi is still 0. So then we get plus 0. And so this is equal to the Laplace transformation of negative sine of pi t. And then that right there will be equal to negative, and then this is a. So negative a over s squared plus pi squared. And that's our Laplace transformation. So now we have that. And then step 4 is to plug into formula. So the Laplace transformation of sine of pi times t, u of t minus 1 is equal to e to the negative pi s, sorry, wrong letter, wrong number, 1. So e to the negative 1 times s, and then times negative pi over s squared plus pi squared, like that. Now, if we were to redo this, and I know I'm kind of going off a tangent here, but just to show you it again, using it the other way, so Laplace transformation of sine of pi t, and then times the step function u of t minus 1. The other way we could have done it is using the original form of the formula, which would be the Laplace transformation of f of t minus a, u of t minus a, which in reality you should kind of always try to use this one. Um, just makes your life easier usually. In this case, usually sine and cosine. This one is typically better for sine and cosine. It's just this one, because it requires you to know trig identities, that's what makes the challenging part. But the actual like simplification was really nice, and it just ended up making it not too bad. But it's just that trig identity fact that is what really makes it actually difficult. So we want to make it look like that. So step 2 is to identify f of t and a. So f of t is equal to sine of pi t, and a is equal to 1. And then step 3, which we're going to do here, is we want to manipulate f of t. Actually, you know what? We're going to do it this way. This is better. We are going to find the Laplace transformation of f of t, like that. So the Laplace transformation of sine of pi t is equal to pi over s squared plus pi squared. And then step 4 is we are going to basically sub in the t minus a. So now we're going to sub in t minus a into f of t. Yep. So we're going to make that manipulation. And then step 5 is we're going to plug into formula. Before I plug into the formula, actually, let me justify why this is the case. Just like we did before in the past, where we do something like t plus pi, or I guess I'll use a number here, t plus 2 minus 2, and then that would allow me to do algebraic manipulations. When it comes to trig, a lot of these changes are kind of justified through trig identities. So the one here that I'm kind of using to justify that f of t, because essentially what I'm trying to say is that uh, I am converting f of t into f of t minus 1. And the way that I can do this is if I were to distribute the pi, there is a trig identity that says sine of, and the formula would be pi, sorry, theta minus pi is equal to sine theta. And that right there is what allows me to justify this change. So that's why I can do this translation and it still be the essentially same function, quote unquote, but the transformation works. And then from there, now we just plug into formula. And so the Laplace transformation of sine of pi t u of t minus 1 is equal to, which we already know. Well, actually, that should be a negative, and that's where we're going to get a negative sign, s squared plus pi squared. And, oh no, sorry. Flip that around for a second. And then I forgot the e, so the negative a, which is 1s. And I believe that's good. Let me just double check. Nope, it was a negative sign. So we just put a negative here. And so that makes a negative. And then that matches what we had earlier. So in reality, I think the first one's actually better now that I think about it. In either case, you kind of have to use a trig identity, which is not fun. So long-winded side example, but that's kind of the most challenging part is taking the Laplace transformation of a step function with another function. You just kind of have to use some of those manipulations. So now we can go back to this and we can plug in negative e to the s, the negative right here, times pi over s squared plus pi squared. And we can evaluate s squared. Well, I'll do it on the next slide. Going back. So s squared y of s minus s times 0 minus y prime of 0, which is 0, plus 9y of s equal to pi over s squared plus pi squared plus e to the negative s pi over s squared plus pi squared. And step number 5 is to isolate y of s. And so we get s squared y of s minus 9y of s equal to pi times s squared plus pi squared. And I could combine these into one term, but I'll just wait. And then I can factor out the y of s. And then now I'll combine them into one. And then we get our final answer. And that is y of s. So one more example of finding y of s. Find y of s for y double prime plus 49y equal to 8t times, sorry, and 40, and then 0 to 5, and then t is greater than or equal to 5. So basically now what happens when it's not 0 on either one, right? So step 1, formula. So the Laplace transformation of y double prime is still s squared y of s minus s y of 0 minus y prime of 0. Laplace transformation of y prime is not needed, so I'll just do y. And that's going to be equal to y of s. And then step 2 is we're going to find the step function. Step function. So f of t right here is going to be equal to the first function minus the first function times its step function at the first number we hit, which would be 5, plus the next number, which would be the step function at 40 times, 40 times step function at 5, right? So when t equals 5, 8t and 8t cancel each other out, and then you're just left with 40. So that is our step function. And then we can simplify it, which we might do later. So, well, actually, this is going to be one of those cases where we will want to simplify it later, but we can kind of show what we're going to do here. Because we have t minus 5 and we are multiplying by a non-constant, we're going to want a t minus 5 with it. So what we could do is notice that these both have u of t minus 5 right here and right here. And I could factor that out. And actually, I'm going to do plus here. Put the negative 8 inside. And then plus 40. Can't forget t. And from there, actually, no, let's leave the negative outside. No, actually, it makes more sense to leave it there. Nope, sorry. Going back and forth with myself. There we go. And so it's 8, and then this will be minus 40. So we factor out a minus u t there. And then from there, I will be able to factor out an 8 from both of them. And look at that. I get t minus 5, which is what I want. I want a t minus 5 to match up the t minus 5. Otherwise, I'd have to go back and do that whole thing where, let's see if I can quickly find an example. You take the number and you add or subtract like I did in, try to find the example where I did it. Thought it was this one. Guess not. Basically, we get to manipulate it by adding and subtracting and then distributing later, so we don't want that. All right, so from there we have our step function. Step 3 is we're going to take Laplace of both sides. So the Laplace transformation of y double prime plus, we'll factor out the 49, really like 49 here for some reason, of y equal to the Laplace transformation of 8 times t minus the Laplace transformation, there's an 8 out here, can't forget about that, of u of t minus 5 times t minus 5. Should have it in the front, that's fine. And step 4 is to evaluate and sub in initial conditions. So thankfully we have zeros and zeros again, so the Laplace transformation will become s squared y of s minus y of 0 minus y prime of 0, but can't forget the s right here, plus 49 y of s equal to 8 times t. Well, t is going to have the factorial thing, so that's going to be 8 times, well, it's t to the 1, so then it goes up by 1. It becomes s squared, 1 factorial in the numerator, minus, and because this is u of t minus a, and this right here is f of t minus a, so it's already has the same value for a, then the formula is just going to be e to the negative, and then whatever a is, which is 5 times s. So unfortunately, we have 5 and s next to each other, times the Laplace transformation of just t, because t minus 5 would become t, which is going to be 1 over s squared, right? Again, comes back to that formula we mentioned at the very beginning, where I have it, I think right here. Nope, wrong button. This one right here. We're using that right there. So we have e to the negative 5s over s squared. Then we are going to sub in our initial conditions. Minus 0, minus 0, 49 plus y of s equal to 8 over s squared minus e to the negative 5 times s over s squared. And then step 5 is to isolate y of s. So then s squared y of s plus 49 y of s equal to 8 minus e to the negative 5 times s over s squared, and then y of s times s squared plus 49 equal to 8 minus e to the negative 5 times s over s squared. And that tells us that y of s is equal to 8 minus e to the negative 5s over s squared times s squared plus 49. Would not be a fun partial fraction decomposition, but nonetheless, we're able to do it here. And we got y of s. So let's do our example where we actually solve an IVP. Solve the initial value problem, y double prime minus 5y prime minus 24y equal to 1, 0, 0, t less than 1, and then 1 is greater than or equal to t. Now in this example, I have introduced y prime, and the reason I didn't have y prime in the other 3 is just because it would have made finding y of s a little bit more time consuming, and we didn't need to go all the way to the very end. So, but this one, since we are going to, might as well have the entire left side have all the derivatives and just kind of remind ourselves of the entire process. So step 1 is formula. So Laplace transformation of y double prime, s squared y of s minus s y of 0 minus y prime of 0. The Laplace transformation of y prime is equal to s y of s minus y of 0. And the Laplace transformation of y is y of s. Step 2 is to find step function. So this whole thing right here, f of t. So f of t is going to be equal to 1 minus 1 u of t minus 1 plus 0. So that's what we end up getting. And so f of t is equal to 1 minus u of t minus 1. Not too bad. And then step 3 will be to Laplace both sides. So the Laplace transformation of y double prime minus 5 Laplace transformation of y prime minus 24 Laplace transformation of y equal to the Laplace transformation of 1 minus the Laplace transformation of u of t minus 1, like that. So we're going to have to take all of those Laplaces. And then step 4, in fact, I might just move that over to the next slide since it kind of looks like it's way too much there anyways. Now we're actually just going to evaluate all the Laplaces. So step 4, evaluate and sub in initial conditions. So s squared y of s. And if you know what the initial conditions are, you can just like, I mean, I could just put 0 now, but because we're learning, I'm just going to do it all. But in practice, I would just plug in the number, especially if there's 0. You don't have to write it all down. And then s y of s minus y of 0 minus 24 y of s equal to the Laplace transformation of 1 is 1 over s. And then if you remember, the Laplace transformation of just a step function is e to the negative a, which would be 1. So negative s over s. That's just the generic formula for it. And then we get s squared y of s minus 0 minus 0 minus 5 times s y of s minus 24 y of s equal to 1 over s minus e to the negative s over s. Thankfully, no 5s except, I guess, this one right here. And then step 5 is going to be to isolate y of s. So s squared y of s minus 5s y of s plus, or no, minus 24 y of s is equal to 1 minus e to the negative s over s, like that. Whether you keep it together separately is kind of a personal preference. In fact, I prefer to keep it separate now that I remember because, and you'll see why, it just makes the inverse Laplace a little bit more manageable, more obvious what it is when it's not separated. And then y of s is equal to s squared minus 5s minus 24 equal to 1 over s minus e to the negative s over s. And then y of s is equal to 1 over s times. Now, if you recognize that you can factor it, then I recommend that you do. Just save yourself the step. But if you can't factor it, that's not the end of the world. It just means you're probably going to have to complete the square later, which maybe is the end of the world then. Okay. But yeah, we've isolated it. So all we have to do now is take the inverse Laplace transformation. But we preemptively think to ourselves, if we know we're going to take the inverse Laplace, but we're probably going to do partial fraction decomposition, unless, of course, you recognize that it's something else. I know that the only time it's going to be sine and cosine if it's like s squared plus a squared, right? Like that's sine and cosine. This is a quadratic. If I get a quadratic in this form, um, let me check to see if it factors, and if it factors, then it has to be with exponentials. If it can't be factored, then it's a complete the square, and then it becomes, again, sine and cosine. So that's what step 6 is going to be. Partial fraction decomposition if possible. Otherwise, complete square. Okay. So y of s is equal to, well, s squared minus 5s minus 24 is going to be equal to s minus something, and then s plus something. Why? Because it's a minus minus. What multiplies to 24 and adds up to 5, essentially? 1 times 24? No. Let's see. 2 times 12? No. 3 times 8? That's a possibility. So let's see, if I do 3 and 8, I get negative 24, but that's a positive 5, so it's got to be the other way around. Right? Again, however you factor, right? So now I got that. Thus, y of s is equal to 1 over s times s minus 8, s plus 3, minus. Now, at first glance, you might be thinking, does this mean I have to do two partial fraction decompositions? And the answer is no. They both have the same denominator. So if you do it for one, you're doing it for both of them, right? So you don't have to do it individually. You're really just doing it as an entire, one. So then 1 over s times s minus 8, s plus 3 is equal to a over s plus b over s minus 8 plus c over s plus 3. And I did plenty of partial fraction decomposition examples in previous videos. I'm not going to do the full-blown like every single step, but I will do some of it. So if I multiply everything over, I get the following, right? Whatever is in the denominator cancels out, and then I'm left with everything else. So I get something like this. Okay. And then I think of the singularity points, what points will cancel out some of the terms. And so then I think to myself, s equal to 0, s equal to 8, and then s equal to negative 3. So if I plug in each of those numbers, they're going to let me solve for one of the variables, right? So just to show you that, let's see if I give myself a smidge more space, maybe. Let's say s equal to 0. If I plug in 0, I'm going to get 1 equal to a times negative 8 times 3, which is positive 3. And then the rest of them are going to be 0. So plus 0 plus 0. And so then a is equal to 1 over negative 24. Here's a fun fact that people often overlooked. Negative 1 over 24 is equal to 1 over negative 24, and that's equal to 1 over 24 with a negative in front of the fraction. You probably forgot about this, but the negative on the fraction doesn't matter top or bottom. It's the same thing. It can be in front. It's just a personal preference. The only time it matters is if there's two negatives, right? Then they cancel each other out. Um, s equal to 8, positive. So 1 is equal to 0 plus b times 8 times 11 plus 0. So then b is equal to 1 over 88, like that. And from that, we do s equal to -3. Again, make sure you're doing it in the order that you wrote down A, B, and C. And then I get 1 equal to 0 plus 0 plus C times -3 times -11. And so a negative times a negative is positive, so C is equal to 1 over 33. So that's my partial fraction decomposition. So this problem basically contains a problem from 6.2, sorry, 6.1, 6.2, 6.3, like as a part. So we're doing whole problems from other sections as a single part, right? So that's kind of like, finding the step function, or sorry, taking the Laplace transformations, that's 6.1. Finding the step function, that's 6.3. And then partial fraction decomposition, that was back in like 6.2, right? I mean, that's just part like 6, right? So that's kind of the magic of all this, is we're just combining everything into one problem. So y of s is equal to -1 over 24. And I always stress, just leave the fraction on the numerator. It doesn't really help you if you move it to the front, because you're going to end up putting it in the front anyway, so just leave it alone. And then -1 over 33. Nope, that's the positive one. This one's, I believe, the negative one, right? Nope, they're all positive. Except that one. There we go. And then step 7 is the inverse Laplace. So the Laplace transformation of y of s, well, that's just going to be equal to y of t at the end of the day. We're going to do the inverse Laplace of 1 over, actually, let's do it step by step here. What was it? 1 over s times s plus, nope, do it the other way. S plus 3 plus, or is it minus? It was minus. The Laplace transformation of e to the negative s over, and then because we factored it, it's going to be the same thing. Like that. So we factored out the bottom, and then through the partial fraction decomposition, we can basically take the Laplace transformation now. So if you combine it together into one, you can do that, but I'm just going to do it on the first one. So -1 over 24 plus 1 over 88, s minus 8, plus 1 over 33 over s plus 3. Not going to touch this one yet because I'm going to use the result from the first one on the second one. But yeah, let's try it like that. And so the Laplace transformation is equal to, so a number over s, that's going to be -1 over 24, because it's just 1 essentially, plus 1 over 88 e to the 8 times t, plus 1 over 33 e to the -3t, right? Here is where it gets a little interesting. So we're going to use that formula that I mentioned at the beginning of class. Hopefully we can do it more easily here, where essentially we have e to the -s times -1 over 24. Sorry, gotta give myself more space. -1 over 24 over s plus 1 over s minus 8, except that's not 1, it's 1 over 88, plus 1 over 33 over s plus 3, right? So like that's what the partial fraction decomposition came down to. And what I'm going to use here is the Laplace transformation of e to the negative as f of t, right? Like we have a formula for that. And that formula was equal to, and just to remind you, we'll go back to the table so we can see it. So when you have e to the at times a function, which is somewhere around here, right here, number 14, it's just the translation. You just shift it over. So we already know what the Laplace transformation is, right? So just to remind you, it's going to be the Laplace transformation of f of t shifted from s to s minus a. Like that's what we kind of talked about in previous sections. So what's the Laplace transformation of all of this? Well, it's just what we have in the left, right? So then this is equal to negative 1 over 24 plus 1 over 88 e to the 8 times t plus 1 over 33 e to the negative 3t minus, okay, 1 over 24 negative, so the numbers don't shift, it's whatever. And because we have the e to the negative s, sorry, I went backwards. We're doing the inverse Laplace. So correction. I forgot to write inverse on all of these. That's why I was not paying attention. These are all inverses. So the inverse Laplace transformation of e to the as times f of t, right? So for a second, I was like, that doesn't make sense. Let's go back to the table. So right here, e to the negative at times f of s, we're going back to the step function with it shifted over. That's what I meant to say is the shift over. And so I was like, where's the step function in my brain? So I knew something was wrong when I didn't see a step function. U of t minus 1. And then it's just basically our answer shifted over by whatever a is. So negative 1 over 24. It's just constant, so there's no shift there. Plus 1 over 88 e to the 8 times t minus 1 plus 1 over 33 e to the negative 3 t minus 1. And that's the final answer. Now, can I simplify this? Absolutely. But this answer is perfectly valid. I can combine like terms, I can factor numbers out, I can do whatever is, necessary. But all in all, this answer is 100% valid. In fact, as I look at the solution, this is the answer that they just leave it in that form. So that's how you deal with an IVP dealing with the step function. It's just a worse version of 6.3. Like that's really what it ends up being. It's just you kind of have to do a lot more in each step. And each step is essentially one whole section in the past, right? So that's what it ends up being. So kind of like a small topic, just because it is covered in the homework. Let's just mention the Laplace transform of periodic functions. Now, I will say that the nice thing about this specific type of problem is that it kind of illustrates what type of functions you would actually be working with in the Laplace realm. Like these are the type of functions that you would run into because the power of the Laplace really comes when you're dealing with integral defined functions. So a periodic function is one defined as, in this case, they're going to do f of, and I think our textbook uses s, but I will use f right here. So f of t plus capital T is equal to f of t. So basically, it's periodic because it repeats itself. So once you get past the full cycle and it comes back, you're essentially at the same function. So it behaves the exact same way. So we use that. In the homework, they'll give you what the period is, and you kind of just uh, go from there. T is greater than 0, where capital T is the period. So an example of that would be something like a box function. So it does this. Oops. So that. So notice that if you look at one cycle, right, and we'll call this like capital T right here, and this is 0, the function basically repeats itself every T. So it's the same function. Between 0 and T and T and 2T, it's the same function. So basically, this allows me to kind of say that this function is the same thing between this period. It just makes life easier for us. That's all it is. It's a convenience thing. So what's the problem with this function is it's not a continuous function, which is always a problem to deal with because there's a lot of jump discontinuities. So the Laplace transformation, actually, now let's use it. So the Laplace transformation is defined as, so the Laplace transformation of f of t in this case, which is just f of t plus t, is equal to, and where this formula comes from is just way beyond the scope of this class, but not anything if you set your mind to you couldn't figure out. So 1 minus e to the negative s times capital T. So that's where the period comes into play. So that's the denominator. And then the numerator is an integral from 0 to whatever the period is, e to the negative s times t, f of t, dt. So that is the Laplace transformation. And as long as you can identify what the period is and then create a step function out of whatever the function is, then you're pretty much good to go. So that's kind of the idea. Well, you don't even have to create a step function. You just got to be able to integrate exponential usually. So we'll do that in our next example. Find the Laplace transformation of f of t equal to 1, 0, if it's defined between 0 and 1, and then defined between 1 and 2, and f of t plus 2 is equal to f of t for all t greater than or equal to 0. So what tells you that it's periodic is the fact that they mention f of t plus 2. So this right here is the period of the function. That's capital T. If I did 3, it would just be t equals 3. So step 1 is formula. So Laplace transformation of a periodic function will be equal to 1 minus e to the negative s times the period, and then the integral from 0 to the period, e to the negative st. Let me make sure it's that t. Yep. And then f of t dt. Step 2, identify t. So t is equal to 2 right there. And then step 3 is to identify f of t. So in this case, we will need a step function. So the step function will be f of t is equal to 1 minus u of t, 1 plus 0 u of t minus 1. Oops, yeah, so 0 at 1, at 2, that's what I meant to say. And yeah, and these all go away like that. Yeah, wait, I did that 1 and 0. First of all, that should be less than right there. There we go. Now I forgot it. 1 minus 1 u of t minus 1, and then plus 0. I mean, the rest of it's just 0. So we have that. So then f of t is equal to 1 minus u of t minus 1. So step 4 is we're going to plug into our formula. I'll go to the next slide. Step 4, plug into formula. So this is where it actually gets interesting, because we have 1 minus e to the negative 2 times s. Let's just do s times 2. And then we have the integral from 0 to 2 e to the negative s t. And then we have 1 minus u of t minus 1, like that, dt. And then we think to ourselves, well, we've never taken an integral with the step function before. Like, how does that pan out? Well, we just got to think about what the step function really is, and then we can kind of go from there, right? So if we think about it, when t is less, sorry, remember, when t is between 0 and 1, right? Our step function is turned off, right? So u of t minus 1 is equal to 0. It's not activated. And then between 1 and 2, our step function is turned on and it's equal to 1. Well, what's 1 minus 1? 0. And what's the integral of 0? 0. So if you recognize that, then this integral will actually become the following. Okay? We're going to break it up into two integrals, like just to really show this. So 2s. The integral from 0 to 1, e to the negative st times 1 minus 0 dt plus 1 minus e to the negative 2s, the integral from 1 to 2, e to the negative s times t, 1 minus 1 because u of t has become 1 dt, and this whole thing becomes 0 because the integral of 0 is 0 for a definite integral. And so what I end up getting is the integral from 0 to 1 e to the negative st dt, which is not a very complicated integral. It's one we've done before, to some degree. So using the fundamental theorem of calculus, we get 1 over s negative e to the negative s times t from 0 to 1. If you're wondering, where did negative 1 over s come from? E to the kt integral is equal to 1 over k e to the kt, right? Plus c, of course. And so if we plug in 1, we get negative 1 over s e to the negative s. And if we plug in 0, I know it's very tempting to think that e to the 0 is 0, but e to the 0 is equal to 1. So then we get minus negative 1 over s. And then if we simplify that, a negative negative becomes a positive, so we get 1 over s minus e to the negative s over s all over 1 minus e to the negative 2s. And that answer is perfectly fine. You could simplify it by combining, but it's kind of up to you at that point. But that is our Laplace transformation.